Well, good morning, everybody, and welcome to Ellensburg, Washington, USA on a Saturday morning. Freezing rain outside, the old family van slipping and sliding on the way to get up here to school, but made it. Happy to be with you this morning. Thank you for joining us this morning. The local time is about 8:50 a.m., and we will begin our program at the top of the hour. That's 12 minutes from now. You know the drill. If you're watching live, we say hi to each other and thank you. We have approaching 300 joining us already here. And if you're watching the replay, yeah, you can skip ahead 12 minutes to the beginning of the program. This is our first of 4 shows devoted to paleomagnetism. And our guest today will be Bernie Housen. Before I email Bernie the invite to join us, are we 5x5? And where are you viewing from? I'm seeing some 5x5s and I'm encouraged by that. Ernest is in Angola, Indiana. Dayton, Ohio, good morning. Red Deer, Alberta. A lot of 5x5s. Okay, I can stop thinking about that. Thank you. Garrett, the Dutch Night Owl from the Netherlands. Hello, Garrett. Warren, Maine. Portland, Oregon. Brussels, Belgium. Derbyshire, UK. Sacramento, California. Glasgow, Scotland. Huntington, Vermont. North Dakota. Unity, Wisconsin. Oh, scrolling very fast now. I just feel like I just want to grab things as they go by. Nanaimo, British Columbia. Yakima, Washington. Estacada, Oregon. Hello. Bath, UK. Sudbury, Ontario. Martha's Vineyard. Gray to match my hair, says IC. Martinez, California. Holden, Washington. Hello from Railroad Creek Valley. That's cool. Nice to see you. Thank you. North Cascades, in the heart of the North Cascades. Prosser, Washington. Kamloops, BC. Bothell, Washington. Portland, Oregon. The Chuckanut, Blodgett, Oregon, Seattle, Washington, Southwest Virginia, many familiar places and familiar names. Always great to have you with us live. Honey Greg says that was a fantastic talk yesterday. Thank you. I thought so too. That was Hannah Shamloo, and that lecture is available to you on the YouTube channel if you didn't get a chance to see it. I thought she did a great job. But we're back to the solo show here with the chalkboards, and I'm needing to take a moment and invite our guest, Bernie Housen. So give me a moment, would you please? Add the guest. Copy the link. It's going to Bernie. And the way that email goes. All right. Oh, yeah, a bunch of people saying Hannah was great. Oh, yeah, I'm glad you enjoyed that. She's just a natural, I think. Yeah, what? In case you're just checking in with us and haven't been with us since last year, I'm letting you know that we are very regimented now for the rest of the alphabet series. Every Wednesday at 2 p.m., every Saturday morning at 9 a.m. You know that by now, but there's no special shows, there's no extra shows. We'll just keep working our way until the end of the alphabet, which will be our last show of this series. The Baja BC series will be Saturday, February 18th. You know, just feel like I need to make sure that everybody's understanding what's going on, making sure that we don't have any miscommunications that way. Okay, we've got about 400 watching live now. Let's say hi to a few more of you. I'm relieved that our technology is working this morning so far. Switzerland. Hey, what's up, homie? Hans-Peter Planzer. I don't recognize your name. I have Swiss heritage myself. Welcome if you're new to us. Liberty Lake, Washington. Menominee, Michigan. Clyde Park, Montana. Kirk and Philomath. Rogue River, Oregon. Jefferson City, Missouri. Good morning. Jacksonville, Oregon. Sequim, Washington. Montlake Terrace, Washington. That's in the Seattle area. I'll scroll back. It was going so fast there for a while. I don't know. What we have? Abu Dhabi. Helpma26 says, good evening from a wet Abu Dhabi, coming in loud and clear here. That's really cool. Hello from halfway around the world. Great to have you with us. West Allis, Wisconsin. I'm way back now. KC is from the front yard of Mount St. Helens in Washington. Billings, Montana. Eagle, Colorado. I'm way back now. Grandpa Carl from the Granger Clay Pits. Yep. Fort Hood, Texas. Yorkshire, UK. Mazama. Nice. All right, well, I see Bernie in the green room. That is great. Bernie, welcome. I'm glad that you're there. So you get yourself settled. Costa Rica, hey, Rick, you're a regular now. Ontario, Canada. Ontario, Oregon. 66KBM says hi from the Netherlands. Hello. I've always had plenty of viewers from the Netherlands. We have Kirk in Sweden. He's a regular. A few people are saying hi to Bernie. That's nice. Scott's in Sangre de Cristo Mountains, New Mexico. Columbia, Missouri. Visalia, California. Next to the SB. Santa Barbara? I don't know. All right. Okay, well, we've got about 5 minutes before we begin. I see Bernie in the green room, and I don't know, Bernie, if you wanted to share your screen and get that in the green room even now, you could, or we could just kind of roll with it once we get you on. But I'm just relieved to see that we're up and running there. That's good. Yeah, let's take just a moment and show you the rest of the month. Regularly as well. I'll do it again in a few minutes when we start the program, but I just thought I would just make sure. So we're going to have Bernie back again on Wednesday. Jane Wynn, Randy Enkin, those are all paleomagnetic people. And then Karin Siglock, and breaking news, we have Mitch Mahalanek, who is able to join Karin in that show. I'm very excited for that. I've never met Mitch. I don't know what he looks like, never heard his voice. So we'll have Karin from France, and we'll have at the same time Mitch in British Columbia. So that'll be an interesting show. Stephen Johnston up in Edmonton, I believe. I'm not sure of that though. And Bob Hildebrand will be joining us twice from his home in Tucson, Arizona. And then you're like, what happens to the rest of the alphabet? Oh, I'm not really sure. We'll just see how things go here for the rest of the month. Okay, greetings from Mexico. Hello, Trex 351, or 531, excuse me. Phil's says hi from the Index Pluton. And Marysville, Washington, and so on. Okay, well, good. So Bernie is not only in the green room, but he's got a shared screen ready to go as well. That's good. And give me an extra moment to get my head right here, and we will begin promptly at the top of the hour. Thank you for joining us. Hot mic. Okay, there's no signs of trouble with the technology. Get that off your mind. So first message to yourself, boy. You don't have to cover everything with Paleomag today. You're going to have Bernie on again, and you got 2 more Paleomag shows. So remember that you're setting the hook with the Mount Stuart Batholith, and you're doing what? You're reviewing some of the basics of Mount Stuart that you know and that most of the audience knows. You're incorporating some of your work this summer, some of your fun with some of the folks out in the field, and some of the questions you were asking. Right, and you're basically asking that of Bernie. You're setting the table for Bernie. He has Mount Stuart Batholith stuff ready. There might be some overlap, so you got to go quick. He might just double down on what you're saying, but I think you need to lay it out in the way that the audience knows it. And then you go to Bernie. Don't forget the laptop. You've got some slides, but keep it brisk as always. And before you start on the chalkboard, make sure you set up at least the basics of what the 3 remaining Paleomag shows will be, so that you can tell your guest as well, like, what our rough plan is. Again, we don't want to feel a sense of urgency where we have to answer every last Paleomag question today. There will be live Q&A. Go to that, use it. There will be tons of questions. And Bernie can handle that. He's handled it his whole career. But you step in when you feel like some of the questions are better for Wednesday with Bernie as opposed to today. You're almost maybe a moderator or a referee today. You can do that. You're not teaching Paleomag today. That's why you have Bernie. What are you doing? You're not teaching Paleomag. Not even close. All right. Why are you walking around in circles? Why is your mouth so dry? That ain't no whale. That ain't no whale. Hello, everybody, and welcome to Ellensburg, Washington, USA. Thank you so much for joining us today for this very special episode devoted to Paleomagnetism with Mount Stuart. Our guest is Bernie Housen, and Bernie is up in Bellingham, Washington this morning, and we will have Bernie back next time as well. So let's go to it right away to set up what we're trying to do today, what we think we're going to be doing with Bernie again on Wednesday. And then again, we have 2 more paleomagnetic shows. And so I want to make sure you kind of know how to kind of approach this with your questions. We will have maybe an extended version of live Q&A with you today. So we have Bernie coming back Wednesday, January 11th. That's 2 p.m. Pacific time. A week from this morning, we will have Jane Wynn. And then the following Wednesday, Randy Enkin. So I'm telling Bernie this right now. I think Bernie knows this. I think the next Bernie show will be devoted to the hit and run paper. And so we'll build off of what we were doing with Basil last show. So if you were really into that hit and run paper, you've got questions about the hit and run Paleomag, I guess I'm asking you if you can put those off until Wednesday. But we are this morning doing basics of Paleomag, and I'm choosing to emphasize Mount Stuart as well as kind of a reason for us to get into the Paleomag instead of just being super general about it. And then if you're curious, Jane Wynn is going to talk about working with Ted Irving, and I can't remember, Mount Tatlow, the Mount Tatlow study, which Basil says is bulletproof from a paleomagnetic perspective. We'll talk to Jane about that, and other studies that she has done. And then Randy Ankin, the following show, the fourth of the 4 Paleomag shows, will be talking about the Carmex volcanics and probably this place called Churn Creek that came up a couple of times with Basil in the last show, and other things that Randy wants to talk about. So that's kind of the rough outline for our 4 shows. You know, and I'll be selecting some of your live questions that, you know, if I know it's going to be useful next time, I'll just kind of move on to the next question. Okay, that's the plan. Let's pick it up and get into this and enjoy Bernie Housen. Here's my approach on what we want to do. Let's start with something that we're familiar with, okay? We're familiar. I started this, session A, do you remember? I started with this at the beginning of the alphabet, right before Thanksgiving. The Mount Stuart Batholith, which is in between my house and Bernie's house. So I am here in Ellensburg in central Washington. Bernie is at Western Washington University in Bellingham. And we're not only talking about Mount Stuart, which is visible from our backyard, but the entire Mount Stuart range, the Mount Stuart Batholith, the Mount Stuart Pluton. That is our topic today. And so in a cross-section, we've done this a number of times. Even last winter we were doing it. We were talking about the relations in cross-section between the Mount Stuart Batholith, which has been radiometrically dated with uranium-lead dates. Those are dates that are 15 years old, relatively new dates. 96 to 91 million-year-old granitic material in the Mount Stuart Batholith. MSB, that's our abbreviation we're going to be using in the papers and also on the chalkboards. Mount Stuart Batholith, batholithic rock. Granitic rock, in case you don't know what a granite looks like. There we go, okay? Good. We emphasized a number of times that the Mount Stuart Pluton, the Mount Stuart Batholith, was magmatic material that invaded from below, and it invaded older rocks. 162 million-year-old Ingalls ophiolite, green waxy rocks, the serpentinite, that were thrust on top of the Windy Pass thrust, and so the ophiolites were shoved up on top of the Chewaucam schist. These are in millions of years ago. So we made the point a number of times that it's not just the Mount Stuart mountain that's potentially moving north, so many kilometers, thousands of kilometers north, it's the country rock as well. And then it's not just that, but it's other portions within the insular superterrane and everything else. So in a way, today we're starting local again, but you know what's going to happen. We're going to be talking about the entire planet today when Bernie helps us see how paleomagnetism works. But I'm starting with kind of a field geology point of view. You know, I've taught field geology for 20 years. That's my comfort zone. I don't know anything about paleomagnetism. That's clear. And the past couple of summers, when I've been up in the North Cascades making videos with Bob Miller and Stacia Gordon and Mike Eddy and others, I keep bringing up Baja BC, and those guys and others who I value, I think that they're open to new ideas. I think they're gentle people. I think they're very careful scientists. Many of them are saying, I don't see how we can use that paleomag and that Pluton. And here's why. And I got into this with Bob Miller on video, and, you know, then visited Merle Beck up at his home, his retirement home, in late August, I think it was. And Merle replied to the comments that Bob Miller and Bob Hildebrand have been saying about the potential folding of the Mount Stuart Batholith. So this is part that Bernie might double down on in just a bit, but you'll hear it from me first. Looking at a map pattern, not a cross-section now, but looking down from heaven on the Mount Stuart Batholith, here's the map pattern. These are phrases that Bob Miller and others were using as they were mapping the details of the Mount Stuart Pluton, the Mount Stuart Batholith. Here's Leavenworth, Washington. Ellensburg is down south off the chalkboard. Here's Stevens Pass, where US 2 goes up and over the Cascades. Snowing up there, I'm sure, this morning. This is the map pattern. And casually, Miller and other field mappers were calling this the portion of the Mount Stuart Batholith known as the hook. obvious name, the stem, where the batholith gets real narrow, and then this big blob on the south end, the mushroom head. Up until Jenny Matzel's work with MIT, why can't I think of his name? Sam Bowering's lab, new dates came through that we have not 93 million year old granite all through the Mount Stuart batholith, but there was generally an age progression of the 96 million year old material up here in the north by Stevens Pass, 93 million years old in this narrow stem, and then the big bulbous mushroom head down by Leavenworth and Mount Stuart summit itself, 91-ish. Okay, let's cut to it. A bunch of folks I've been talking to who don't know much about paleomag but know a lot about field mapping say, this thing has to be folded. Look at this pattern. That hook is a hook because there's a fold axis going through the middle of Stevens Pass. It's an anticline where not only this granitic material was folded, but the older Chewacam schist, that 120 million year old stuff, which is mapped all through here. There's all sorts of strikes and dips within the Chewacam that look folded as well. In fact, this is a plunging anticline to the northwest, and both limbs are dipping to the northeast. So these folks are saying, okay, you're taking all this paleomag from the Mount Stuart batholith, but the thing's been folded. You can see it. Okay. Went back to Merle, talked to some others, emails with a few folks that know the ups and downs of what's going on there, and the age of the granite is not necessarily the age of when the magnetic grains are preserved or fossilized or locked into the granite for all times. And now I lose credibility with Bernie and others who are watching and know the details of paleomag. So I'm going to try to share a couple quick things, and then I'm going to go to the laptop, and then I'm going to Bernie. That's basically all I'm doing here, is just to get us going. Do I have anything else? Oh yeah, I got one more thing. So Merle's been watching some of these programs, and occasionally he'll email me very generously to kind of keep me on track. And so when I keep talking about these grains being locked into the granite as the granite is cooling, Merle says, well, I got a little quibble with that. Nice job in general, but I have a quibble. The grains don't physically align themselves with the magnetic field. Actually, those ferromagnetic grains are frozen in place long before they are cool enough to become magnetic. 500 degrees or so, often less. And what happens is that they align their magnetic moments with the field by a complicated process called thermoremnance acquisition. I don't have the background to totally get what that is, but I'm just sharing some phrases to get us going with Bernie. From the major paper that I'm going to share with you, the 2003 paper that is available to you right now, I'll show it to you in a sec. While I have this on the board, this is Bernie and Merle in their 2003 paper saying they've got these dates of the granite, but the age of paleomag signature is 90 million years old in the south. I'll use their words. Down here in the mushroom head in the south, the magnetite cooled below the blocking temperature at that time at 90 million years ago. Paleomag directions were acquired within 0.5 to 1 million years of 91 million years ago. I'd like to hear more from Bernie about that in just a second. And something even a little bit more perplexing to me, up here in the older part of the Mount Stuart batholith, in the north, in the hook, up there's both magnetite and pyrrhotite, and we cool below the blocking temperature of magnetite at 86 million years old, and below the blocking temperature of pyrrhotite at 83 million years ago. Is that what I think it means? That we have magnetism for as recently as 83 million years ago? From the pyrrhotite, I need to learn more. But here's the payoff. With all these papers from Merle and a few papers where Merle and Bernie were overlapping, and that's where we're going to start, Bernie. I want to hear your history about when you arrived at Western and how you overlapped with Merle. Here's the payoff. The most current, I think, understanding of the Mount Stuart Batholith is that 90, not 96, not even 91, but 90 million years ago, the calculations by Merle and Bernie tell us that the Mount Stuart Batholith was at this latitude, paleolatitude of 31.3 degrees north, plus or minus 8 degrees. I think that's what that means. Like potentially 39 degrees north or potentially 20, whatever. And here's the present latitude of Mount Stuart Batholith. So there, that gives us a northern transport, the whale moving north and rotating clockwise, by the way, as it moves north, a grand total of 2,900 kilometers north, plus or minus 600 kilometers. That's where we're heading. Let's switch to the laptop, do a couple quick things, and then it's on to Bernie. So cameras seem to be working, nickzentner.com. Look what I have for you here. I have 10 papers, and I want to explain. The one that we are sinking our teeth into today is the top one, the most recent one, from 20 years ago now. Mount Stuart again, that's my title, Bernie Housen and Merle Beck. And if we open it up, American Journal of Science, and there's a whole team of authors, including Russ Burmester and others. Dave Tucker, I noticed that name. And here's the gory detail that I'm trying to just whet our appetite on, including the paleolatitude and other things. Whoa, whoa. But there's plenty to enjoy, and to be honest, I've kind of forgot about this paper. Otherwise, I would have used it this coming summer when I was asking Bob Miller and others about the hook and whether Mount Stuart was really folded or not, and how valuable that is. So there's a paper that is combining map patterns, bedrock geology, and Paleomag from 20 years ago. Okay, why are there 9 more papers? Well, last summer, when I was starting to talk to Merle about this series, I said, Merle, I want to read what I can about your work. And there are dozens of papers. Let me come back here. And Merle was really great by email. So I only met Merle 3 times. I was filming each time, you know. But the emails and a couple of phone calls here and there were really helpful. And I said, how can I use your work, Merle? How can I share your papers? And he said, well, I don't know. I guess just put them all up there. And I'm like, well, God, that's like, I don't know, more than 30 papers, Merle. I said, would you please just think about this? This is back in July, I think. Would you please think about this and come up with your top 10, like a David Letterman thing, your top 10 papers? And he put some thought into it, and he eventually got me to his top 10 papers that were representative of his career. And those are the 10 papers that are waiting for you. And I'll let those speak for themselves. And we may or may not dig into a little bit of those in the next few shows. Back to the laptop for a couple of slides, and then we're coming to Bernie. Great. Yeah, I mean, I'll show you one other one. So this one here, 1976, is the one that broke this concept wide open and got all the traditional geologists in a tizzy. And I think out of all the papers, it sounds like Merle was most proud of this one. 1976, American Journal of Science, discordant paleomagnetic pole positions as evidence of regional shear. And so even maps like this, we need to understand from Bernie. Okay, so that's at the website. Let's put that away. I did grab a few things to finish setting the table for Bernie, and then we go to him. So for those in distant lands, this is what Mount Stuart looks like from my little town. I mean, it is majestic. Come on. I've already shared this photo a number of times, but this is the crystalline core we're talking about. And this is the mushroom head. This is the southern part. You're looking north right now. So this is the southern part that's apparently specifically 91 million years old and has magnetism set up in it a little bit younger than that, 90 million years ago. And remember, now this is the thing that, according to the Paleomag, was almost 3,000 kilometers south in Mexico 90 million years ago. Another favorite shot taken by Tom Foster from our valley of the granodiorite or different kinds of granitic material in the Stuart Range. And then here's the Ingalls ophiolite. Here's the 162 million year old stuff in the foreground. Backcountry Lindsay, I shared this once before, but if we train our eyes, here's the hook. So the color that is on this map for the Mount Stuart Batholith is this, whatever this is, peach. So here's the hook, and Lindsay's giving us more precise dates from Jenny Matzell's 2006 paper from the Sam Bowering lab. Here's the stem, and Lindsay has a whole series of photos that if I had more time, I'd share all those photos. Great job, Lindsay. Yes, if you're interested, there are 2 full interviews with Merle, August of 2020, and then another one August of 2022, just a few months ago. And the first time I met Merle was, I'll tell you about that in a second. So here's the original paper. We just celebrated the 50th anniversary of the original paper, and you remember meeting Linda Nosen, his graduate student. And, you know, we can barely see the hook here and the stem and the mushroom head. You can kind of see it on the map pattern. And there were just a few sampling locations of the Mount Stuart Batholith. 10 years later, here's Merle himself giving us a more revised hook, stem, mushroom. Those are my words that I added, of course, and additional sampling locations. Mount Stuart Batholith continued to be his most interesting work. He kept coming back to that throughout his career. And then here's the recent paper where we take the original sampling sites, the Beck and other sampling sites of 1981, and then Bernie is going out with Merle and others, and they're sampling again. And they're checking and rechecking those measurements. And that data still holds up 20 years later. Now, this is Darrell Cowan in 1994. You might remember when I had him on session B, and I said, do you remember anything about this? Why did you write in your 1997 paper, Darrell Cowan, why do you have this magnetization age that's younger than the rock? He's like, yeah, I don't remember the details of that. Huh. Well, we're finally talking to an expert about why these numbers are younger than the rock itself, and other commentary on that. Again, here's the 1976 paper that I think, Bernie can correct me, but I think was the most important perhaps of his papers. And then again, here's the 2003 paper where Bernie and Merle are joining forces, collecting 20 new paleomag sites. And declination, inclination, other things I don't understand. Oh, you know what? I was going to do that before I finish up with the slides. Give me one more moment. Just another way to set up Bernie. Here's what we're faced with here. Now, I'm not saying we're going to go through each one of these with Bernie in just a second. I get the general idea of inclination measurements giving us paleolatitude of a particular batholithic body, or sediments in the Nanaimo or something else. I think I also get the general idea of declination giving us the potential of measuring clockwise rotation as this block is moving north. So in other words, get the inclination of the paleomag to help figure out how much the whale has moved north. Look at the declination of those grains to figure out how much the whale has moved north and also rotated clockwise. Mount Stuart in the caboose, Baja BC block, or a bunch of smaller whales, you know what we've been doing. But does Bernie want to talk about remnant magnetization? Do you want to ask about remnant magnetization? Paleomagnetic pole position, I think that's going to be especially helpful next time. The Curie temperature for minerals. Geomagnetic secular variation, in other words, the movement, the annual movement, the wander, I guess that's the phrase for it, of the magnetic field. Magnetic north keeps moving. It's heading towards Siberia, I guess, in the last few years. Does that screw up everything? These are, I think, common questions that Bernie's been asked a million times. And are you aware, Bernie, that the magnetic field has reversed off and on over the years? Of course he has. I'll just leave that there. We might refer to it on occasion. Final couple of slides, and a 5-minute warning, Bernie, less than that, and I'm coming to you. So the first time I met Bernie and Merle was in 2014. And we started making these short PBS episodes. And the producers said, well, what's your first episode? I think we should do paleomagnetism and Mount Stuart. And they're like, what? And so here's Chris Smart, the guy that I did the programs with. It's a series called Nick on the Rocks. So if you type in a search box on YouTube, Nick on the Rocks, Mount Stuart, you'll find the short episode that I did with Merle. And so I drove up with Chris Smart, and we filmed Merle in the Western Washington University department. This is the fall of 2014. And we got way too much footage. These episodes are only 5 minutes long. We probably filmed an hour. And I remember we filmed Bernie a bunch, and we never even, Bernie ended up on the cutting room floor. I still feel bad about that, Bernie. So I'm trying to make up for that today and next Wednesday. But here are the cores they have from the Mount Stuart Batholith in the lab today up at Bellingham, Western Washington University. Here's an old shot of Merle out in the field, I think in the early 70s. Here's Merle more recently with a student. And Bernie sent this to me just the other day. I believe this was up at the Nanaimo, and they were taking drilling for paleomag from the Nanaimo. In southern British Columbia. And Merle was just such a natural on camera. Like the director immediately said, boy, this guy is good. We just got to keep going with this guy. He was just so charismatic. And again, we filmed way too much. I should try to find that old footage and reuse it somehow if we can still find it. But yes, Merle back on the left, Bernie Housen on the right. And I think it's time to go live to Bernie at his home. Let me get my headphones. Battery 100%. Okay, that's promising. Let's cross our fingers and try to bring in Bernie. Bernie Housen, how are you today?
All right.
It's great to meet you. Well, thanks for joining us today. What's the weather like up there?
Oh, it just started to rain.
Okay, yeah, that's a
rain in Bellingham in January. Imagine that.
That sounds about right. Yes. Well, we've got freezing versions of that for sure. I think your audio is okay, maybe a little bit low, and I don't know if I can do anything about that on this end. So yeah, maybe a little closer to your
get closer to the mic. I think that should. How's that?
I think that's better. Thank you very much. Can I ask a couple personal questions first of all? When did you arrive at Western Washington University?
So I was hired in 1997. So I was at the University of Minnesota as a postdoc at the Institute for Rock Magnetism. Okay. Was there for 3 years. So I think I got here the summer before, classes start. So when you're hired, you're usually hired, effective September 16 of that year or whatever. So I think we got here in July.
And do you remember that you were competing with that job with a bunch of other folks who have this specialization? Or did Merle kind of handpick you for the job, or did you have a connection with Merle back then?
Well, so, it was a super competitive job. Very few faculty positions for, paleomag specialties at that time. And, even now they're rather rare. Huh. So it's kind of a minor miracle I was hired. Although, I'll say I'm worth hiring.
Yeah.
I had met Merle the first time at a meeting in Baltimore, like the year before. So it must have been like 95 or 96 or something like that. Yeah. And I was introduced to Merle by Rob Coe, who I knew well. So he's a paleomagnetist, retired, but he was at Santa Cruz. Mm-hmm. And just met them, and I think got to talking, and they were going to go to a baseball game in Baltimore. And I was like, I'm a baseball fan. So Rob Coe, Merle Beck, myself and Vincent Corrillo, who's a really famous, paleomag tectonics person in France.
Yeah. Oh, okay.
We all went to a Baltimore Orioles game. I forget who they were playing. But my job was to explain American baseball to Vincent. So it was pretty fun.
You were working hard, I'll bet. To try to explain
that Merle was a great fan of baseball and the Mariners, and so that was anyway. So that's when I met Merle.
Okay, well, thank you for sharing. How about one more before we get into the details? So when you arrived, Merle had his Paleomag lab going for 20 years, I guess, or something like that. Did you offer some skills or something different that Merle was not doing?
Yeah, so I mean the lab that was there at the time. Most of the instruments that were being used were the original ones Merle bought with his startup, like 1970. Right. And they're still working. We still actually have those instruments, and we can get them to work if we really wanted to. And then we had Russ Burmister's a really good scientist, but also he's a good technician, and he built an oven. And you have to building these ovens to thermally cook these rocks is kind of tricky, because if you think about your basic physics, if you have a coil of wire, you put an electrical current in it, which is how you make a furnace, right? So what happens when you have a coil of wire with an electrical current? What happens?
I don't know.
It makes a magnetic field.
Okay.
and so you have to wind the coils in the oven in a special way so that each coil's magnetic field cancels out each other's.
Oh, wow.
Yeah.
I had no idea. Okay. Yeah. So yeah, there were improvements there. And I'm guessing that in the last few years of Merle's working career and your first few years there, that's why you were putting out these papers together, or not necessarily? It was all you and he were just kind of using Merle's data? Or were you
no. Merle retired the same time I was hired. That's how how things work.
Yeah.
And he was super active though. I mean, so it was almost like having another postdoc, because you have this pretty substantially accomplished senior scientist who's retired. Yeah. So my role was, I work in a broader range of rocks. Merle worked mostly with igneous rocks for two reasons. One is that they're better recorders of the magnetic field. Mm-hmm. And the other is that, they're more strongly magnetic, which the equipment that the lab here had was more amenable to work with. So before I even arrived at Western, I wrote a proposal to get a superconducting magnetometer, which is one of the things that you saw, and we built the shielded room and got new equipment. And so, essentially we, went on a crash building spree of, transforming the lab from a 1970s lab to a 21st century lab.
That must have been so exciting. And one of the offshoots of the new work and the new equipment is that it essentially agreed with Merle's stuff from the old lab, more or less.
Oh yeah, I mean this is a great example. I'll show you some of the figures from that paper, but yeah, there's a lot of talk in the big picture science world about reproducibility and things like that. The different studies of the Mount Stuart Batholith are a really excellent example of how, in this case, we're able to successfully reproduce and improve the robustness, I guess, of results that were, done 50 years ago now. So,
wow. Well, thank you for all that. I think it's helpful just to kind of get a sense of the backstory there. Can I bring in your slides and let's just see if we can just kind of go for it? Is that what you'd like to do right now?
Sure. I'm okay. A little uncertain where to go for. I have a whole thing where I can explain, as many gory details about paleomagnetism as we want, but I'm going to start with this mineralogy and Curie temperature, I think.
Good. Let me bring it in. Okay, that's, are you seeing, I'm just curious, can you see both of our heads plus your screen?
I can.
Okay, good. Well then, yes, please. And you know that I'll occasionally just kind of butt in, and I might do this and just put that away. Yeah. And you can see us, you can see our two heads going back and forth right now. Okay, good. So I think I'm so excited now. So yeah, let's just roll with it. Just Bernie, however you want to do this, that'd be just great. Thank you.
All right. So we're going to put our petrologist hat on, or our solid state physics hat on. And let's talk about magnetite. So the little, kind of green and blue box, magnetite, it's a, in terms of mineralogy, it's an inverse spinel. So that's its structure. So the basic chemical formula of magnetite, as everybody knows, is Fe3O4. If you break down how the type of cations to make that balance, you end up having two Fe3 pluses and one Fe2 plus. Okay. Mm-hmm. And a spinel mineral has two different cation sites, an A site and a B site, and then it has the oxygen for the anions. And so the way this works is that we kind of have two things going on. So the bonding that takes place with the iron, it produces an arrangement of the d orbital electrons, so that they're each in a individual orbital, or not space, right? So there's 5 spaces in the d thing.
Yep.
And they all spin. The electron spin in the same direction, so they're unpaired. So you just put in these electrons in the d orbitals. So the Fe3 plus has 3 and Fe2 plus has 2. Okay. Right? Yeah. When they're in this spinel mineral, the geometry of the crystal lattice is such that the electron spins are actually linked together in a process that's called exchange coupling. And the only thing we need to know is that all of the electron spins in the A site will spin in the same way, and all of the electrons in the B site will spin in the same way, but they're going to spin in the opposite direction. Mm-hmm. So A and B will spin oppositely to minimize energy. Okay? So all those arrows are you have spinning electrons are going to make a magnetic field. So there's a spin moment that we would call that.
I see.
And so if you add up the up spins and the down spins, you're going to see that there's a net, down, 2 electron spins spinning down. So that's what gives magnetite and any other permanently magnetic material its ability to be a magnet.
Okay, I'm going to hold you up for just a sec. This is great, but I need to come in. And so what state is the magma in physically during this story so far? Are we slushy? Are we? Yeah, or
this is all solid. This is all solid, right?
Okay.
So the mineral is a solid crystal.
So in the case of the, go ahead.
Yeah, we're not getting at the petrology of how it is in the Mount Stuart rock yet.
Okay, good. All right.
Let's keep going. Get to that in a second.
Thank you.
Okay. So essentially it's the way in which the electrons are in the spin in the crystal lattice that gives these minerals their magnetic properties. Okay.
Thank you. Yep.
There's a relationship between the magnetic property and composition, both with the different cations, but also with the different minerals. And that has a big effect on like the intensity per unit lattice, but also other properties like temperature dependent properties. And so when we talk about the Curie temperature, I have another slide that will also kind of show this in a little bit more detail.
Good.
The magnetic properties are a function of temperature. And so it's essentially a magnetic phase transition where above the Curie temperature, the electron spins spin randomly and can be realigned with any change in the magnetic field. So nothing would be recorded.
Okay.
Below the Curie temperature, the energy of these electrons is enough to hold a magnetic direction. So it's sort of like, you know, among the older folks in the audience, if you have a VCR and you hit play, or if you have a cassette tape and you hit record.
Yeah.
Right? So when the mineral is below this Curie temperature, you can hit record. Above it, you're hitting erase. You're not recording anything.
Got it. Got it. That's helpful. Really helpful.
So yeah, so the little graph on the left are the vertical axis is magnetization and the horizontal axis is temperature.
Okay.
And so these are different permanently magnetic minerals. So we see magnetite. Let's see if this pen will work. Oh yeah. So here's magnetite, right?
Oh, nice. Yep.
So it's Curie temperature. So when it reaches this temperature, magnetization is 0. And so above that temperature, this mineral won't be able to record any magnetic field.
600 degrees centigrade. Okay.
Yeah, 580 basically, but yeah.
Okay. Yep. All right.
This other mineral, pyrrhotite, is an iron sulfide, Fe7S8. So that has a much lower Curie temperature. Oops, on a bad drawer, but here we go. 310.
I love the red. I love this. This is great.
Right? Okay. And then if you have hematite, that's Fe2O3, that has a Curie temperature that's almost 700 degrees C.
Okay.
All right. So we really need to know, in order to interpret the magnetic history, what minerals are carrying the magnetization. On the right, we have, if you're a petrologist, you like ternary phase diagrams and things like that.
Oh boy.
And we know about solid solution, right? So, so that means you have basically the same crystal lattice, but you can substitute different cations. So in this ternary diagram, here is magnetite, Fe3O4. And it forms a solid solution with this other mineral called ovospinel. Okay. So you can have any combination where we're substituting some titanium for the iron. You can do the same thing with hematite and ilmenite. So here's hematite, and here's ilmenite. So the rhombohedral iron titanium oxides. And over here, this is the valuable diagram. So these contours, the 600, 500, and so on, those are contours of Curie temperature that are influenced by this solid solution. So, a mid-ocean ridge basalt also has iron titanium oxides because they're more mafic and everything. They're going to have more titanium. And so they have Curie temperatures that are, sort of in this, 300, 400 range.
Okay, we're heading somewhere. I can tell. I can tell. I want to detour you, but I don't, because I want this to continue. So you know where I'm ultimately wanting to go with the Stuart problem. So please continue. I'm loving this, Bernie. Thank you.
Yeah. So let's what do we need to know for paleomagnetism, right? So what are the magnetic minerals? How are they petrologically related to the rock? So in the case of Mount Stuart, we need to know, when did those things grow from the magma? And things like magnetite, they have a very high melting temperature. So they form really early in the crystallization process. Most importantly, we need to know what is the thermal history of the Mount Stuart batholith and its possible chemistry, right? And then we can figure out how the magnetic field was acquired and also when it was acquired. So these are the sort of questions as a paleomagnetist that we always have to ask ourselves whenever we're doing any study of any rocks. All right, so let's talk about this thermoremnant magnetization. So this is the mode of magnetization that Mount Stuart acquired its record of the magnetic field. It's the most faithful mechanism to record the magnetic field. It has the best basis in physics. Louis Néel won the Nobel Prize back in the day for figuring this all out for magnetic properties. What we're going to be looking at is how the magnetization is acquired when it cools below this Curie temperature. Okay. This can happen with a volcanic rock when it cools at the surface, so an eruption. So, where you are, you're surrounded by the Columbia Plateau basalts. And so when those basalts flowed over the Earth's surface and when they cooled off, they recorded the magnetic field. Your granite that you showed for the Mount Stuart, that's a plutonic rock, so it cooled underground. And so the magnetization of an intrusive rock is going to be acquired more slowly. And in some cases, it's acquired only after, we have uplift above the ambient temperature at depth.
Oh, yeah.
Right?
Huh.
The other thing is that, magnetization can be reset if things are heated back up. So we have to be, cognizant of that. And as I mentioned, this is all recorded by internal electron spins. So it's all about those electrons inside the crystal lattice.
Was there any of that with the Mount Stuart Batholith, the remagnetization?
Well, that's a good question. So when we get to that, we'll talk about what's the deal with the pyrrhotite, right?
Okay.
So, yeah.
All right. Let's go back.
But the gist is that when we look at the ages, there's a different thermal history in what you've called the hook and the mushroom part, and that's the kind of most important take-home point in interpreting the magnetization of Mount Stuart.
I mean, I just have to say it. I mean, I'm an idiot for doing those videos this summer and not just thinking to look at what you guys had been doing. Like, it is all there in the abstract in that 2003 paper. Like, I just forgot about it. So the way you laid it out is, I need to keep going back to that paper, but you're getting us even more interested in digging into that paper. So
it's a super long paper.
Well, that's okay. We got time. We got time. Okay, Bernie, keep it going, baby. I love this.
All right. So here's a little slide that has a few figures. It has a untidy equation that tries to explain how this thermoremnant magnetization works. Okay. So up here's a little graph that is just showing, the magnetization versus temperature. It doesn't have any numbers on it. I guess that's called a Caltech graph. Anyway, I digress. I jest. All you Caltechians, I'm jesting with you all. So above the Curie temperature, we're not recording the magnetic field. Below the Curie temperature, we are. Okay. Little cartoon, right? So here's the magnetic field direction, this arrow right here. So above the Curie temperature, the type of magnetic behavior we would call paramagnetism. And I explained that in some other slides that I didn't start with because we don't really care about that too much right now. But I can explain that to anybody's heart's content later on. The magnetite is still there. For something like a granite, let's just say this is at 650 degrees. All those minerals have crystallized. This is a solid. It's just at high temperature, right?
It's crazy. Okay, yeah.
And so the thermal energy is enough to randomize the magnetic directions. Okay. And then when we cool below the Curie temperature, the kind of internal energy for the magnetic order is enough so that it can retain the magnetic field. So as the minerals cool from above to below the Curie temperature, once you hit the Curie temperature, it's like hitting record on your VCR or your cassette tape. Okay.
Sure.
This is just another cartoon showing the same process, but this equation here, this is for what we'll call relaxation time. That's this letter tau. That's a Greek letter tau, if you can't recognize that. I draw them weird. All right.
Thank you. Thank you.
So what the tau is if you have a bunch of these magnetic particles, you magnetize them, you let them sit around, things want to randomize over time.
Mm-hmm.
And so the relaxation time is how long it will take for these things to just randomize. So we lose the record of whatever magnetic field they have. Make sense?
Yep, it does. It does.
Okay. So you can solve for that with this equation. And I don't want to explain all the parts and the gory details, but basically, the top part right here of this bit is magnetic order. So H is a magnetic property of the mineral. So it's like the amount of magnetic field it takes to flip any direction it would record using just a magnetic field.
Mm-hmm.
And if you want to see how that works, I have some other slides I can show you later on. Okay.
Mm-hmm.
M sub S is the strength of the magnetic field that, like per unit crystal lattice or whatever,
Mm-hmm.
how strongly magnetic it could be. So magnetite is very strongly magnetic because of that 2 electron spin moment.
Okay.
V right here is the volume of the particles. So the size of the particles.
Mm-hmm.
Okay. And then down here, the terms are simple. So T is temperature, 2 is the number 2, and then the K is the Boltzmann's constant. Okay.
Okay.
And so when you see KT, Boltzmann's constant times temperature in any kind of physics equation, that usually represents thermal chaos.
Okay.
So the way this works is that when thermal chaos is high, so when temperature is high, when T is high, relaxation time is low, and you can reach a point where relaxation time goes to 0.
Huh.
That's kind of how it works.
I got some of that. I lost it a little bit towards the end, but I think to get it going for me, is it possible to do 1 or 2 more steps to get to what I had on the chalkboard with did we know that why we have these different numbers for age of the rock versus age of mineral magnetization?
Yeah, let's just go to the Mount Stuart stuff.
Thank you.
Okay.
I don't mean to push you along. I don't mean to rush you, but
Yep. No, we got it. We got a good flow of this thing here. Yeah. Here's this wandering of the magnetic field. All of this, okay. Right? Okay. So here we go. So some figures from the original 1972 paper. Mm-hmm. But let's go to this figure. So this is a colorized version of that same, figure from the 2003 paper that you just showed. Mm-hmm. Right. So the little red dots are the new results that we collected. And I just want to point out that, the whole long list of co-authors, those are all students in a class, a paleomagnetism class that I taught at Western.
Oh, wow.
And so we go around and try and collect samples early in the fall and then work on them in the quarter and then try and have a result. And so I thought, well, we're coming up on the 30th anniversary of this important paper. There are some questions about, what Daryl Cowan was talking about. The reason for his question mark was some work done by Scott Patterson and Steve Lund at USC, where they found evidence for a different magnetic mineral, pyrrhotite. So they were finding that the magnetic directions were being removed at about 300 degrees. And that's pretty important in a, intrusive rock that has a complex thermal history, right?
Yeah. Yeah.
most of the, well, almost all of the work that Merle did in his lab used an alternating magnetic field to isolate the directions. It's a different technique, and it doesn't give you the thermal information that, you know, allows you to more closely link the Curie temperature and the mineralogy with what is carrying the paleomagnetic signal. So I think in terms of our understanding of you know, this Pluton and its magnetization, that's the most important contribution, is that we have a lot of good thermal data, and so we can really link the petrology with the magnetic direction.
So perhaps for the last 25 years, you've heard from geologists who said that Pluton has to be folded. Look at that map pattern. Was that an open thing with you and Merle? Like, yeah, of course it was folded, but we've got this data that is younger than the folding. Or was that not like an open discussion with you and Merle about the folding business?
Oh, it was an open discussion, but, you know, we knew that the folding takes place at temperatures higher than the Curie temperature.
Right.
So it doesn't matter. If you look at this site, here's another little background. So if you look at the way that we label our sites, the first digits are the year that they were collected. You see some that are 92.
Oh yeah, yeah.
So I actually collected those samples in 1992 as a PhD student at Michigan. Oh. The idea was to look at using a different set of magnetic techniques to look at the structural foliation, if you will. So using anisotropy of magnetic susceptibility to actually look at the pattern of emplacement and deformation and perhaps this folding business, right? So this was a, you know, I started the study, but, you know, as PhD students are wont to do, you have things that you just don't finish.
Right.
So I hauled those rocks from Michigan to Minnesota to Bellingham and then got them all out. And the class, we went out and collected some new sites. And we also worked with the existing set of samples that I had.
So especially those red dots, it looks like you were in the Icicle Canyon. You were maybe heading up towards the enchantments almost, like but still pretty close to a road of some sort. You're not backcountry hiking.
We didn't do a lot of backcountry stuff, no.
Yeah, too much equipment. Okay.
Well, and you know, for the class, all the 01s were the class collected ones. We just did this in a day.
Oh wow. In a day, okay.
Yeah, no. So we left at like 4 a.m. and from Bellingham and drove out there and let's start here and start there and, you know.
Wow.
Yeah.
Well, that's a cool. I didn't even think that a bunch of those authors' names were students. I mean, that's really cool that you were teaching and also kind of contributing to this big paper. So I love that.
Yeah.
So here's my question to you. It's not a geology question. I think I want to go to some viewer questions in the next 10 minutes. And then we can also think about which of what you have we can do also on Wednesday when you come back. So do you have something that would kind of get a little bit of closure on what we're doing right now before we go to some viewer questions that will be all over the place?
Yeah, no, let me go to.
I appreciate you being so willing to just kind of go by the seat of your pants here, Bernie. Thank you. Oh, wow, terrific! Look at that. Wow.
So there's this one. So let's start here, and then I can work back a couple. Okay.
Good.
So here's the most important part, I think, about the thermal history. So as part of this paper, we compiled all of the existing thermochronology. And so what that is it's a recognition that in isotope systems such as potassium argon, or now we take the hornblende or the biotite and we send it to a reactor and compare argon. So we call that argon, but it's basically radioactive potassium decaying to argon. The argon can be lost. And so there are thermal effects that are it's a different process, but it's rather analogous to the concept of blocking temperature or acquisition of magnetization. So if you take a amphibole, a hornblende from the Mount Stuart, and you heat it up, it's going to lose its argon, its radiogenic argon, and the age will be reset. And so in many cases in plutonic rocks, the argon ages can be cooling ages and not not crystallization age, right?
Yep.
Okay.
Yep.
All right. So there's a real difference in the thermal chronology between the southern half, what you've been calling like the mushroom, I guess, and the northern half, which is that folded hooky thing. Okay.
Yeah.
So I have a box. So this plot is plotting the age, and these ages are from the thermochronology, from argon in hornblende and argon and biotite, and in uranium lead. Not up to date with the Matzel's dates, but the uranium lead ages don't really matter because they're happening at really high temperatures.
Yeah. Yeah.
Right. So
that's important. I got to keep thinking on that. But yeah, it doesn't even matter how precise those dates are if you're that hot. Wow.
Right. Okay. So the other thing is that in order to use the inclination of the magnetic field to estimate the latitude that they were magnetized in, you need to know paleohorizontal. You need to know what horizontal was at the time of magnetization. Right?
Yes.
Okay. So for the Mount Stuart, Jay Ague and Mark Brandon, they used a barometry technique. So you can look at the details of the composition of different minerals or mineral combinations and thermodynamic stuff to get a pressure, which can be used to get a depth, which if you have a pattern can be used to make a surface of paleohorizontal. So they did that to try and address the paleohorizontal problem in Mount Stuart. So this blue bar right here, where I say it's the ALNH closure, that's the temperature range in which the aluminum in the hornblende barometer acquires its pressure estimate. So that blue bar is the vital information about paleohorizontal.
Oh.
So what we want to be able to demonstrate is that the magnetic direction was recorded as close to that time as possible. And we see from that blue band that if we're being, if the signal's carried in magnetite, it's too high, right?
Yep.
It would be awesome if there were hematite in these rocks, but there isn't. It doesn't work that way.
Right.
Okay, so the yellow boxes are just means, averages of the amphibole and the biotite, essentially cooling ages. And so I just drew a red line connecting the dots. So that's the time temperature diagram for the Mount Stuart. Okay. In the gray, I have a bar for magnetite and for pyrrhotite. And so those are the temperatures where those two different minerals would acquire their magnetic signal. So from this, we can see two things. Well, three things. One is that the age of magnetization of anything recorded by the pyrrhotite would naturally be younger.
Yes.
Than anything that would be recorded by magnetite. And that the thermal gradient is pretty steep, and there's not a huge gap in time between the aluminum and hornblende closure and when the magnetite signal would be acquired. Okay.
Yes.
The other take-home point is that, and the metamorphic petrologists from looking at things like the Chihuahua schist and stuff like that, the northern part of the batholith has experienced, more metamorphism. So it has a more complicated thermal history than the southern half. And, there's this one outlier here. So what I did, this little dotted line is just, let's ignore that point because I've got a PhD. I can do that. And so this little orange dot right there.
Yeah.
That's what I think the gradient is. And so this is the basis for saying that in the northern half, in the hook, the magnetization age is younger. And in the southern part, it's older. And so for interpreting these data in the context of this Baja BC thing, I just say no to the northern half.
Okay.
The reason I do that is because we've lost our link to paleohorizontal.
Ah.
So I'm being more conservative with the data by recognizing that we no longer have as good of control on horizontal for the data from the northern half.
Mm-hmm.
So let's not use it.
But the southern half you like, and there's not even that obvious folding pattern. I don't know if that matters or not, but in the south.
Yeah, there's so if we, let's see. This is nice. So this is a figure from the paper. It's in color though, but it shows the different directions. So the original study in green right here.
Mm-hmm. Yep.
This one here is the 94. So the Scott Patterson's work with the pyrrhotite.
Yeah.
This is the 1981, and this is the 2002. And then we can look at, like the scatter of the directions. So if the magnetization was acquired and then the rocks were folded, the directions would be kind of streaked out. They would they would definitely show that. And if we wanted to look at that, I think you would want to look at the magnetite carried directions from the hook and any of the pyrrhotite carried directions from the hook and compare what they would look like, because the 300 degree, they probably, none of them would probably show any kind of folding in the magnetic directions, because that process happens at a much higher temperature.
Well, I mean, and that last part, I guess it feels like oftentimes my discussions with other geologists is they're just thinking of the Mount Stuart Batholith in a vacuum, and that these signals are just this one pluton. And I guess this is more of what we'll do next week, but all these other Cretaceous plutons are having similar patterns. Like it's not just this individual pluton. Merle was up and down 2 continents doing some of this.
Yeah,
work.
well, and there are some plutons that are more complicated. So there's a really nice paper that Bob Butler wrote on the Extol pluton, and it has a huge swath of different directions that are the result of deformation. And it's as obvious as day. Yeah. And so you can see when, that's a messed up pluton that's been deformed. We're not going to use it.
Yeah.
Right?
Yeah.
Could be because it's not telling us there's no good link between horizontal and inclination. If we don't have that link, it's not going to be a robust indicator of where these rocks were when they were magnetized.
Okay.
I would say that these are some really, really, really nice paleomagnetic results. This is about the best kind of thermal demagnetization that you can get. We have this really abrupt unblocking temperature. These are just lovely results. So.
Well, Merle kept saying that in the few times that I visited with him. He's like, you're not going to get any clear signal. Those directions aren't going to be any better than in that Mount Stuart batholith compared to all these other batholiths. And you're saying the same thing. Like it's clear as a bell. What makes Mount Stuart batholith so perfect in its plots compared to some of these others. Do we know that?
Well, I mean, you know, I think that, you know, it's mafic enough that it's got good magnetite. So, you know, sometimes if you have like a 2 mica granite, if it's really felsic, it doesn't have as much magnetite, and you might have a poorer signal. Some of these plutons have complicated histories. If they're really deep, you know. So oh my gosh, I'm forgetting the Black Peak batholith is a lot more complicated.
Okay, well, I just think this is wonderful, and to me, this feels like a natural place to stop. I don't know about you, if you've got a couple other things, but can we just kind of...
That's fine. The only, let's see, you know, this is just you know, looking at the metamorphic history and the relaxation time, but we kind of explain that. So yeah.
Well, you know, we're going to open it up to the viewers, and that might bring us right back to some slides you have. You know, I think your slides are working great. I can just keep bringing things in when you feel like you're answering things, but I want to involve the viewers if you don't mind. Do you have another, I don't know, 15, 20 minutes, Bernie?
Yeah, I'm at your leisure.
Okay, thank you. Viewers, thank you for hanging with us. It's 8. We have more than 800 live with us. I see Basil's in the chat. That's nice. Guy Cooley, a few other geology names. Uppercase, please. And these don't have to be long answers. Bernie would just kind of rapid fire, however you want to. You know, this isn't the first time you've had people asking you questions about Paleomag. Toughen Up Fluffy asks, how does Bowen's reaction series affect the timing of magnetization?
That's a good question. So with Bowen's reaction series, the thing to keep in mind is that the melting temperature, crystallization temperature of magnetite is even higher than olivine. And so the iron oxides are going to be, you know, able to crystallize out relatively early. Most of the, you know, history of crystallization that happens in Bowen's reaction series and analogous things for felsic rocks, again, this is all at temperatures that are above the Curie temperature. So those are the petrologic origins of the minerals that carry the magnetic signature, but they're not saying anything about the timing. Now, it's important though, if you can link the composition and type of mineral carrying the magnetic remnants to the petrographic origin, like from Bowen's reaction series.
Okay.
That gives you confidence that those minerals were there from the start, and that you could be recording the cooling, you know, as those magmas cool, you could be recording the magnetic field. So for things like the Columbia Plateau basalts, you know, you would want to make sure that you have, you know, enough titanium in your iron titanium oxide to make sense for that mafic composition.
Great. Let's keep rolling. Greg in East Tennessee wonders, has this detail of sampling been done in the Baja region where this stuff supposedly came from?
So there's there could be a whole other, there are plutons in the peninsula ranges, and these have been studied. Some of them have been studied with, you know, the hornblende barometry. There are the same kind of questions we have for the Baja Peninsula and its possible translation that we have here. To my knowledge, though, we don't have very many paleomagnetic studies that really link the thermochronology with the magnetic signal. So that's something where I think, you know, we can do a little bit more of.
Sure. Both Thomas and Jim have questions that I'm sure you've gotten a bunch. Thomas asks, how does Paleomag account for magnetic reversals? And Jim asks, how to adjust results with a wandering pole.
So Paleomagnetism accounts for magnetic reversals kind of in the sense that that's how we know magnetic reversals happen. So we record that process. So let's see.
Yeah, let's do it.
Let's go.
He's got slides, everybody. He's not afraid to use them. He's got the slides.
Right? So here's the magnetic field. So the field originates in the core. It varies over different timescales. This is just a clip from a Nature paper. You know, the magnetic field moves around. And so this short-term variation is called paleosecular variation. And we need to account for this in any application of tectonic paleomag. So the way it works could be summarized by this figure. So all those little black and open circle dots, so like, you know, this one right here, right? Mm-hmm. So that is the north magnetic pole from an individual lava flow from somewhere in Idaho, because this is a paper that Lisa Tokes wrote on the, you know, around the craters of the moon, the volcanic rocks that are associated with the Yellowstone hotspot. Okay.
Okay. Yeah.
So each one of those recorded the position of the magnetic north pole when the lava flow cooled. And so she sampled a whole bunch of them. And the idea is to look at the geometry of the magnetic field over shorter time periods. Okay. The red diamond is the average of all of those poles. And so the fact that the average pole position, magnetic pole position, coincides with the geographic North Pole, leads us to this simpler geometry for the magnetic field that we call the geocentric axial dipole. And so what that means is that if you average out that short-term variation, you know, that we saw going on like this.
Yeah.
You have to average that out, and you need to sample between 10,000 and 100,000 years worth of time to account for that variation. When you do that, the average pole position gives you the spin axis. Therefore, the average position in ancient rocks gives you the ancient spin axis. But we have to make sure that we've sampled a range of time that allows us to do this averaging.
Yeah.
And the little open circles here, these guys, those are reverse polarity poles, where these are, instead of the North Pole, it's the South Pole for comparison. And so when we look at reversals, you know, the geometry is basically the same.
Great job. Let's keep it going. Pat Miller, you might have a slide for this one too, Bernie. How does magnetic orientation specify the latitude?
Okay, so how does it specify the latitude? It goes back to that geocentric axial dipole concept. Okay. So these are just the spherical trigonometry things, right? So this is the site. So we have the latitude and longitude of the site using the you know, right kind of equations. We take the sample out of the rock and we measure it with our magnetometer, and we get a declination and an inclination. We calculate the North Pole. Okay. So what we do, so with the geocentric axial dipole, I'm just going to say it's the GAD, there's a simple relationship between the inclination and latitude. Sorry. So inclination and latitude. Oops, that's a really bad. Let's try that.
We got you. No, that's a slick writing tool you got there. This is great. This is a first for us. Thank you.
There we go. So that's basically how that works. Okay. And so this is a fun little thing. So this is a set of results for North America. So we get rocks from the craton here, 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 and here. They have all of these magnetic north poles right there. Okay. Average them together, you get this magnetic north pole. Because of the geocentric axial dipole hypothesis, this means that right here is, I'm just going to label it NMP.
Okay.
That's the north magnetic pole during the Cretaceous with respect to North America. So if we wanted to know where the continent was at that time, all we do is we move this to there, and we move the whole continent with it. And so this is a reconstruction of the craton for that time.
That's beautifully done. I've never seen it just simply like that. Thank you for that. That's beautiful.
It's also handy because when we talk about the Baja BC idea and how far away those rocks were, we have to know a reference frame, right? And so in this case, we're concerned with how far were those rocks from where they would have been during the Cretaceous, right? So here, so if we put a little dot right here, that's about where Mount Stuart would be if it were attached to the craton during the Cretaceous.
Oh, over on the right, did you make that dot over on the right globe?
Yeah, I did. It's right.
Oh, right there. Got it. Yeah. Okay. Oh, wow. Okay. That's
so it should be at like 60 degrees north.
Because North America was farther north as a whole.
Farther north. Yes. So the translation, the amount of displacement and the amount of rotation is compared with this basic framework.
Is that what is known as expected direction when you have craton?
That's right.
And
that's right.
Okay.
Yeah. Yeah. So we can then take, right. So we've moved this whole piece of real estate.
Yeah.
And so then you can say, all right, well, you know, if I'm right here in Ann Arbor, Michigan, what would the paleomagnetic inclination be? And so you can figure that out.
Oh God, we got to do more of that on Wednesday. I mean that, and we are. You've got maps just like this in the paper, and that's good. Let's save more of that. But I'm loving that right there. Thank you. Shay asks, is there any evidence to question the geocentric axial dipole theory?
Well, that's something that we're working on all the time, right? So we want to make sure that this is valid. So that paper, this this one here, this was done in 2003. So by looking at the shape, the results from younger rocks like this, we can continue to test and validate this simple idea. There are other more complicated things we can talk about. So one question is, when did the Earth's magnetic field start? When in Earth's history? When was it a geocentric axial dipole? And then to what extent, so the Earth's magnetic field has higher order geometries. So in the present magnetic field, the dipole component of the field is about 90% of its strength and geometry. And then you have the octopole and the quadrupole parts. So, and they're the remaining 10%. Has that been the same throughout time? Those are things that are continually being tested. The challenge, though, is that in order to test those ideas, you have to have a good distribution of data on the surface of the Earth, and you have to know where those rocks came from. And, we use the paleomagnetism to reconstruct the continents. Right?
Yeah.
And the other thing that is also worth pointing out is that one of our most valuable records of from the transform faults and the magnetic anomalies, the ocean basin record of 70% of our planet, right? That's all gone. That does not exist for ages older than 170 million years ago.
Right.
So we don't have spatial coverage for 70% of the surface of the Earth for anything older than 150 MA, basically. And so that does introduce a little bit of uncertainty. And so when we talk about things like true polar wander and ideas like that, it might not be a coincidence that many of those come from times like the Precambrian, where we just don't have as much data.
Wow, fascinating. How about one more, and then I've got a couple final questions for you, and then we'll call it a day with you, Bernie. I really appreciate your energy and your time. Question from Cosmic Aliveness. Bernie, how do you know the Earth didn't flip and the poles stayed the same spot? I assume they're talking or referring to the reversals.
So the Earth, essentially, it's a time scale problem, right? So we can look at volcanic rocks or sedimentary rocks where we have a pretty continuous record of the magnetic direction through a reversal. So the reversal process takes a pretty short amount of time, a few thousand years. There's really no mechanism to adjust the whole lithosphere of the planet. So that would be something called true polar wander, where the entire solid Earth moves as one. There's just no way to do that in a very short period of time like that.
Mm-hmm.
And it would have to go back and forth hundreds of times.
Yeah. Okay, I can't hold it. I got another one here from a geologist. Sky Cooley wonders why, this is maybe out of your league, I don't know. Why would folding of the Mount Stuart Batholith have occurred early and not later as it moved north?
So the idea is that the folding of plutonic rocks occurs when the rocks are still able to be ductilely deformed. So it's essentially a material property of the feldspar and a little bit of quartz, but mostly the feldspar. And so it has to be warm enough, hot enough to be viscous to allow for the thing to be folded like a sheet of paper. If this happened at a lower temperature, it would all be brittle deformation. So it would be broken up by little tiny faults and things like that. So you'd see a very different structural style.
Wow, I never thought of that.
So like mylanites and other things that you see, all the SC fabrics and stuff like that, right? In a deformed metamorphic rock.
Yeah.
Those are all solid state deformation that's happening at higher temperatures.
Wow. That's such a perfect answer. And, I shared with the group when I started this series that I kind of have this hokey numerical scale, like 1 to 10. And if you're a 10, you want 3,000 kilometers of northward movement. If you're a 1, you're a fixist, whatever. And I said at the beginning of the series, I'm an 8.5 because I have these lingering thoughts like when Silesia, this huge Silesia thing comes in and slams into the Pacific Northwest, why aren't we deforming the Mount Stuart Batholith again and screwing up the Paleomag or whatever? But you just commented on that. We're not folding that Batholith. I think that's what you're saying. It's all strike slip at that point.
Yeah. Well, and the other thing too, and I haven't, I could fire up another PowerPoint, but
I'm sure you could.
one of my first students looked at the Cooper Mountain Pluton.
Okay.
Eocene, right?
Yeah.
Its paleomagnetic pole is exactly where the paleomagnetic pole for North America is.
Yeah. that's what I wanted to finish with. So a couple things, and then we'll just kind of riff off of this, and then I promise we're done. So one, I'll just say screwy. We don't have these screwy paleomagnetic signatures in every pluton in the state of Washington of all ages. It's just this time window. You're just talking about Eocene plutons that have no significant, that's basically what you just said, right? No significant translation except for being part of a clockwise rotation, maybe. Yeah. So my question is, well, no, I don't want to go in that direction, but I think possibly people are thinking it's just these guys at Western. I don't know what's going on in their lab, but like it must just be their readings. But can we put a bow on this? Like it's not just your lab. There's worldwide agreement with many of these processes, these techniques, these results. Is that one way that you comment on some of these questions?
Yeah, I mean, a couple of things. I mean, you know, the lab at Western, this has sort of been the bread and butter. I was actually concerned when I got here because, you know, Merle had been hard at work for 30 years, basically, and Ted Irving had been hard at work. And between the two of them, what was left to do?
Right.
You know? Right. But there are other groups. And so when Jane and Randy talk about the Mount Tatlow rocks and some of the things that they did with Ted, if the Mount Tatlow study, if the Wynne et al. 95 study had been done in 1972, we wouldn't have a controversy.
Oh, wow.
There's no way to really impeach the interpretation of those results that this is a tectonic signature.
Interesting.
And, you know, if you read the succession of Mount Stuart papers, you know, the complications of things like tilt and different magnetization ages and deformation, those were all discussed. So it's not like, you know, we weren't all aware of it.
Right.
When I was a PhD student at Michigan, Ben Vander Pleim, who was my advisor, and Rob Vandervoo, they were working on terrains in the Appalachians in Newfoundland and Nova Scotia and stuff. So they were finding displaced terrains using paleomagnetism. Nobody really has a problem with that. You know, so this is a problem that's kind of unique to our area, where if we talk to paleomag folks or tectonic folks throughout the world, they're like, why are people so skeptical about this? Because this seems like a pretty solid set of data. And, you know, we can talk about the kind of social parts of science and speculate why that is, but that.
Well, yeah, let's so I'm just thinking out loud, and we can email a little bit back and forth between now and Wednesday if you like, but I'm thinking I would like to hear a little bit of the social stuff from you and your interactions with people during your career. And obviously we're going to be digging into the hit and run paper. I guess those two themes are what I'm thinking about. And then as I watch the replay of this, if there's tons of other questions that everybody's asking and we just didn't get to, we'll toss those in as well. But
yeah,
I just think this worked great. I don't know how you feel, Bernie, but I just thought this was just ideal for what we wanted to do here today. And I really am grateful to you for it. And
yeah.
Did you want to say anything else before we say goodbye today?
Well, I mean, I think I'd just like to bring up the kind of somber aspect of this, right? Yeah. So, you know, I'm sad to say, and some of you might be hearing this for the first time, but Merle passed away just a couple of days ago. And, you know, it's a great loss for our community, our profession. I think some of the things that Nick talked about where, you know, Merle was just so engaged and eager to share his, you know, wisdom of, you know, working on these problems for 50 years or more. You know, he started doing paleomagnetism in the early 1960s as plate tectonics was being figured out. And so we've really lost a huge legacy but Merle's ability to explain these concepts, his enthusiasm for this, I think, and this should, strike you, Nick, as well. You're at a similar kind of university. We don't have a PhD program here. Merle taught 6 or 7 courses a year for his whole career. Thousands of students, all while doing all of this research. And so his ability as a teacher shows through. And that's something that we've really lost. And so, yeah, it's kind of a sad time for me and for the folks up here. And it's a significant loss. Yeah.
Well, that's beautifully said. Thank you for adding that to this show. And given the circumstances, especially grateful to you for being with us this morning. And I don't know, you can change your mind about Wednesday if you want, if there's lots going on up there. But
I'm game for this, and
okay.
That's one of the things that Merle was always like, when are you going to talk to Nick on his show?
Well,
so here we are.
Here we are. Okay, well, have a good day and a good weekend, and I look forward to visiting with you again on Wednesday, Bernie. Thank you so much. Goodbye. A toast to you for joining us today. A toast to Merle Beck. And a toast to Bernie Housen. Quick story, and then I think we're done for today. I did not know Merle well. I met him for the first time, as I told you, from the laptop in 2014. Drove up there and met Bernie and Merle for the first time, and they were gracious to spend time with us and get filmed for this very short PBS episode, it turned out. But I knew how naturally gifted Merle was on camera, and so it's not an accident that I kept coming back to him. I understood that he wasn't going to be with us forever. I was also just naturally interested in his 50 years worth of work that was still not really being read or talked about by a lot of people in geology that I respect and admire. So that was part of my draw as well. But he was very supportive. I'm talking about Merle Beck now. He was very supportive by email, and he was watching many of the things, including these alphabet things. So last thing I'll say is that Merle broke his hip or femur, or I'm still confused about which bone he broke. I've heard 2 different stories, but anyway, he went into a rehab facility. That must have been in late November, possibly. Many of you know that, and he showed up in the live chat a couple of times from his hospital bed or recovery bed or something like that. And my point is, he was engaged right to the end and was watching each of these shows. And when I would be done with a live stream, I'd get an email from Merle. He'd have some feedback for me. And he's the guy that suggested 2 shows with Bernie, not just one. There were 2 phone calls with Merle just before Christmas, and he was looking forward to these January shows, and he was going to get a new laptop that he could type up some of his personal recollections specifically for our series. And then I guess right after Christmas, things went downhill in a hurry. So Merle did pass away on Wednesday of this past week. Here's to Merle Beck. Our next episode will be Wednesday, January 11th at 2 p.m. Pacific time. Who will be the guest? Bernie Housen. And you've already heard about the general thought of what we will want to do. And then I hope that you continue with us through the rest of these shows in January, and then that will get us into February. One last comment, if you look in the link below this window in the episode description, I put a link for a very in-depth paleomagnetism textbook written by Bob Butler. And Merle suggested that I read that to get deep into the basics of paleomag. I made it about 4 pages, I have to say. It's heavy going and challenging for me. But that link for Bob Butler's Paleomagnetism text, which is online and free, was specifically requested by Merle Beck. Thanks, everybody. I love you. Thank you for joining us, and we'll see you Wednesday. Goodbye from Ellensburg, Washington, USA.